Janko Stennder will present his work for 30 minutes about operators in pre-Riesz spaces, and he will start in 4 minutes. So, Janko, thank you for your patience. You can start.
All right, thank you. First of all, I want to thank the organizers for the opportunity to give a talk here at this conference, which I enjoyed a lot so far, and I also learned much. And I really hope that you will learn something during my presentation. The title of my presentation is Operators in Pre-Riesz Spaces, Moduli and Homomorphisms, which is a result of joint work with Anke Karlauch from the Technical University of Dresden, which is also my supervisor, and Onno van Gaans from the Universiteit in Leiden, which is basically my co-supervisor. And apparently, this works. Okay, perfect. I want to give you a quick overview about what I'm going to talk in this presentation. First, I want to give a short motivation, why we considered all what we considered. And in a second section, I want to give a short introduction to pre-Riesz spaces, although you already heard some of it in the talk of Zalina, and also about Riesz-star homomorphisms, and to recall the definition of order unit spaces and some results there. And in the third and fourth section, I'm going to present the new results, which can also be found in the paper I just submitted together with Anke and Ono at the journal Positivity, and it's also accepted now. So yes, hopefully it will be published soon. So let's begin with something everyone is hopefully familiar with. That's the notion of the Rees homomorphism, or the vector lattice homomorphism on vector lattice. And so those are the linear operators which preserve the lattice structure. And it is well known that those are exactly the positive disjointness preserving operators in vector lattice. And on the other side of this scheme, we have the order continuous Rees homomorphisms, which are known to be exactly the complete Rees homomorphisms, which are just linear operators which preserve sets with infimum 0. Now my ring just went off. I think it's a postman. I can ignore that for now, I think. And we have the relation that every complete Rees homomorphism is always a Rees homomorphism, but it's also known that the converse is not true. And in the past few decades, generalizations of those Rees homomorphisms to partially ordered vector spaces have been introduced by Van Handel, and also Buskes and Van Roy introduced one notion. And in partially ordered vector spaces, the picture looks like this. So we also have on the one side the Rees homomorphisms, and on the other side the order continuous Rees homomorphisms. But the picture is not yet complete. We have this one implication which is still open, so it's not known whether order continuous Rees homomorphisms and complete Rees homomorphisms really coincide, and this question we are going to answer in this talk. And on the other side, we have the different notions of generalizations of Rees homomorphisms. For once we have the Rees homomorphisms, we have also the Rees star homomorphisms and positive disjointness preserving operators. And we have the following implications here. And we also have that the converses are not true in general. And also, of course, every Rees homomorphism is not an order continuous Rees homomorphism. And also those converse implications here we're going to investigate during this talk. So let's now begin with some definitions. We begin with the definition of a pre-Riesz space. Those are just the partially ordered vector spaces, which can be order densely embedded in some Riesz space. So I have some Riesz space Y in a positive linear map, such that the image of X of my partially ordered vector space under this map is order dense in Y, which is also equivalent to having a Riesz space Y and such a bipositive linear map, such that also the image is order dense in this vector lattice, and the vector lattice is generated as a Riesz space by the image, which means that this Riesz space is just, or every element in this Riesz space is just the difference of finite suprema of elements in this image. And all those Riesz spaces where X can be order densely embedded and where the Riesz space is generated by the image are always isomorphic, and they are called the Riesz completion of X. And every Riesz space where the image is just order dense will be called a vector lattice cover of X. And the notion order dense here is not the same as usually used in vector lattice theory. When we say that the subspace Z of a partially ordered vector space is order dense in X, we just mean that every element in X can be written as the infimum of all elements in the subspace which are above this element from X. And some very basic properties about pre-Riesz spaces is that every Riesz space is of course a pre-Riesz space, so it's a reasonable generalization. And also we know that every pre-Riesz space is actually directed, and every Archimedean directed partially ordered vector space is pre-Riesz. And from this property we already get some, like, quite a big collection of examples, two of which would be, for example, the vector space of all polynomials on the compact interval 0 to 1, or also the k times continuously differentiable functions on the compact interval. Those are both pre-Riesz spaces as they're Archimedean and directed. Yes, next I want to introduce all the different generalizations of Riesz homomorphisms in directed partially ordered vector spaces. So we just have a map, a linear map between two directed partially ordered vector spaces. And this map is called a Riesz star homomorphism. If for every non-empty finite set, we get the following inclusion here. And in upper U always denotes the set of upper bounds of some set in the partially ordered vector space, and upper L denotes the lower bounds of some set. So this is quite yes, let's say technical statement, but we will characterize Riesz star homomorphisms in a way nicer way in a bit. And yes, the second generalization is also called Riesz homomorphism. I think Buskis and Van Rooij also called it a weak Riesz homomorphism in their paper, which yes, this linear map has to satisfy this inequality of upper and lower bounds again. And one can easily see that if the partial ordered vector space is a vector lattice, then this coincides with the usual definition of a Riesz homomorphism. And
sorry,
one can define.
very brief question.
Yes.
You just said inequality, but I see an equality here.
Oh yes, yes. It's an equality. Sorry.
Equality is right. Okay, thanks.
Yes. Thanks. Was a mistake. I'm sorry. And yes, the third generalization, which is a generalization of complete Riesz homomorphisms, can be defined in exactly the same way. If I have a non-empty set which is infimum 0, then the infimum of the image of the set is also 0. And now to the characterization you already saw in Salina's talk as well of Riesz star homomorphisms. So this theorem kind of justifies why Riesz star homomorphisms have a special place under those generalizations. Namely, if I have two pre-Riesz spaces with their Riesz completions, and I have a linear map between the two pre-Riesz spaces, then this linear map is a Riesz star homomorphism if and only if there exists an extension to the Riesz completions, which is a Riesz homomorphism. And this extension is also unique and will be called the Van Handel extension of T, because this theorem was found by Van Handel in his PhD thesis. Those Riesz star homomorphisms have a really special role, as we just saw, but they're still not really well studied. Only in the case of some special pre-Riesz spaces, we have a nice representation, namely in the case of order-dense subspaces of continuous functions. This representation is reminiscent to the representation we have in the vector lattice of continuous functions on compact house of spaces. And this is exactly also the way how you can prove it, by using the extension property of Riesz star homomorphisms. But let's now have a look at this representation. If I have two non-empty compact house of spaces and two order-dense subspaces of the continuous functions on those house of spaces, and I have a linear map, then under some mild technical conditions on the space X, I have that the linear map is a Riesz star homomorphism exactly when this operator is a weighted composition operator. So I have some weight function and this map alpha between the compact house of spaces, which is continuous as well. And this linear map can then represent it in this way. Yeah, so this is a really nice result. This is one of the few cases where we actually know how the Riesz star homomorphisms look like. And furthermore, we can also characterize the complete Riesz homomorphisms on those spaces. So X and Y are again order-dense subspace of continuous functions. And when my operator is given in this weighted composition formula, then T is a complete Riesz homomorphism if and only if this alpha satisfies some technical condition, namely if it's weak open on the set where the weight function is strictly positive, And weak open here means that for every non-empty open set, in the set where the weight function is strictly positive, there exists some non-empty and open set such that the image under alpha intersected with this open set is again dense in the set. So in the case of subspaces of continuous functions, we can completely characterize Rees star and complete Rees homomorphisms, which we will later use in a lot of our results. Lastly, for our introduction, I want to remind you all of the definitions and like basic results in order unit spaces. If I have some partial order vector space, then an element is called order unit if for every element in the partial order vector space, there exists some positive lambda such that X is in the order interval of minus lambda U and lambda U. And if this partially ordered vector space is in addition Archimedean, then we can define a norm on this space in this way. So we take just the infimum of order lambdas such that X is in this order interval. And such a space, so a space which is Archimedean and has an order unit, will be called order unit space. And it is easy to see that every order unit space is actually a pre-Riesz space because it's Archimedean and directed. And order unit spaces are really like the basic objects to consider when you want to investigate like Rees star homomorphisms and the other generalizations, because they have a really nice vector lattice cover, which I'm going to shortly outline here. The vector lattice cover, which will be given by a space of continuous functions, is constructed as the functional representation, which was done by Caddison in 1951. So if we have an order unit space with some order unit U, we can define the weakly star compact convex set big sigma as all the positive continuous functionals which map U to 1. And then define lambda as the set of extreme points of sigma. And then if we take the weak star closure of lambda, this is again, this is a compact Hausdorff space with a weak star topology. And the map phi, which maps the space X into the continuous functions on the closure of lambda, which does nothing else than just mapping an element X to the point, to the evaluation of X of each functional. This map is actually linear and bipositive. And then Anke, Bas-Lemmens, and Onno van Gaans proved that this functional representation is a vector lattice cover of the order unit space. So this means our order unit space can always be seen as an order dense subspace of some continuous functions. So on order unit space, we can actually always use this representation of Rees star and complete Rees homomorphisms, which I showed you earlier. And for order unit space, you also already have a nice characterization of functionals, which are Rees star and Rees homomorphisms. So if we have some order unit space and we take some phi from this sigma, then it is already proven that every element in the lambda is exactly a Rees homomorphism, and every element from the closure is always a Rees star homomorphism, and conversely the same. So for order unit spaces, you already know all the Rees homomorphism functionals and also Rees star homomorphism functionals. So back to our picture. First, I want to investigate whether the converse implication of implication 1. So if every order continuous Rees homomorphism is always a complete Rees homomorphism, and maybe you already had this thought when I showed you this slide. We have a characterization of the Rees homomorphisms. We have characterization of Rees star homomorphisms. So where's the characterization of complete Rees homomorphisms, which are functionals? So that was our first step. to investigate this implication, and we began by investigating the order-dense subspace of continuous functions. So if I have some order-dense subspace of some space of continuous functions and take a functional which is just given as a point evaluation for some point in the Hausdorff space, then this functional is a complete Rees homomorphism if and only if the singleton P is open in the compact Hausdorff space. This is just a corollary from the representation of complete Rees homomorphisms on continuous functions. And by means of the functional representation, one can formulate the same now for order unit spaces. So I have an order unit space and its functional representation, then some map in the closure of lambda is a complete Rees homomorphism if and often only if the singleton is open in lambda bar. And from now on, I'll formulate most of the results in terms of order-dense subspace of continuous functions. But of course, there's always an equivalent formulation for order unit spaces. But I will drop this here for the sake of time. But you can find all those results in our paper, and I'll also upload an extended version of the slides so you can see all the results for order unit spaces as well. Before I can conclude that the converse implication is actually wrong, we need this short lemma, which says that if I have an order unit space X, then every positive functional on X is continuous. And if I have a finite dimensional directed partially ordered vector space with closed cone, then every continuous function on X is also order continuous. So this we need to find a counterexample for this implication. And now I drew a little picture of the ice cream cone, which we already had in I think actually 2 different talks already. So this is the ice cream cone in R3. And I think it's well known that dual cone of the space is actually the ice cream cone itself again. And the sigma is this green disk here, so it's just a unit disk in R2, or it's homomorphic to this. And one can easily see that lambda, so the extreme points of the set sigma, is the circle, and that the circle is also closed. So lambda equals lambda bar. So if you now just take some arbitrary element in the set lambda bar, then we know that since the ice cream cone, the space with the ice cream cone is actually an order unit space, that this functional is continuous. And since it's also finite dimensional and the directed partial order vector space with the closed cone, then this functional is also order continuous. And we have proved that every element in lambda is a Rees homomorphism. So this is actually an order continuous Rees homomorphism. But we see immediately that it doesn't matter which point I take, it's not open in lambda. So it's not a complete Rees homomorphism. So by this example, we just showed that the converse implication here is actually not true. Yes. The second step now will be to investigate under which conditions the converse implications which are in general not true, so that every Rees star homomorphism is a Rees homomorphism, or every Rees star homomorphism is a complete Rees homomorphism, under which conditions this is true in order unit spaces. And we found the following theorem. If I have 2 order unit spaces with their functional representations, then I have this, that every Rees star homomorphism is actually a Rees homomorphism between those order unit spaces if the lambda 1 is closed, which basically means that every Rees star functional is also a Rees homomorphism in the first or in the domain. And secondly, I have that every Rees star homomorphism is a complete Rees homomorphism if lambda 1 bar is discrete. So, which basically means that every Riesz star functional as a complete Riesz functional. So this we found in all unit spaces, but as I just said, one could easily formulate this for arbitrary pre-Riesz spaces, that the functionals satisfy this property, but we don't know this yet. So maybe that's an open question, if this also holds in arbitrary pre-Riesz spaces. So we get the following picture. We have that a Riesz star homomorphism is a Riesz homomorphism under the condition that the lambda is closed, and every Riesz star homomorphism is a complete Riesz homomorphism if lambda bar is discrete. So the last implication which is open for our investigation is whether or under which condition every positive disjointness preserving operator is a Riesz star homomorphism. And for that, I want to remind you of the definition of disjointness in partially ordered vector spaces. Namely, in partially ordered vector spaces, two elements x1 and x2 are called disjoint if the following equality of upper bounds hold. So if the upper bounds of x1 plus x2 and minus x1 minus x2 equals the set of upper bounds of x1 minus x2 and minus x1 plus x2, which is just basically, yeah, just generalization of exactly the same notion as in vector lattices. And if I have a linear map between two partially ordered vector spaces, then we call it disjointness preserving if it preserves disjointness. So if two disjoint elements get mapped to two disjoint elements, and the observation that not every positive disjointness preserving operator is a Riesz star homomorphism was already made by van Imhoff in his PhD thesis. But we state here an example that it's not even true when the range space is the real numbers. For this, we take the so-called Namioka space, which is just a subspace of the continuous functions on the interval -1 to 1, which satisfy this equality. Then we can define a functional in this way, which is basically just evaluating at some points and adding or subtracting them. This by the property or by the definition of the space is easy to be seen. It's easy to see that it's a positive disjointness preserving functional, but using the representation by van Imhoff for Riesz star homomorphisms on ordered and subspaces of continuous functions, we can see that it's not a Riesz star homomorphism. So now the question is, which condition on a space do we need that this implication holds? And we found the following condition, which we call property SD for separated by disjoint elements. So if we have some non-empty compact Hausdorff space and some subset of the continuous functions on this space, then X is said to have property SD if for every two distinct points, P1 and P2, we find two positive disjoint elements in X, X1 and X2, such that X1 of P1 is not equal to 0 and X2 of P2 is not equal to 0. So every two distinct points can be separated by two positive disjoint elements. And under this property, we actually get the converse implication. So if we have two ordered and subspaces of continuous functions, then every positive linear map between those spaces, which is disjointness preserving on the positive elements of X, is actually a Riesz star homomorphism. So the final picture looks like this. The implication here holds under the assumption SD. And in our paper, we also investigated whether this property SD is actually necessary, but it turns out it's not. So it's not yet the best property or the right property maybe, but this investigation was quite technical, so I'll omit it here, but if you want to have a look, I'll put it in the slides, and it's also on our paper. Yes, that was everything for the homomorphism part. And we end the presentation with the modulus part. Namely, we figured out the characterization of elements for which the modulus exists in pre-Riesz spaces. Because as I already said earlier, every Riesz space is a pre-Riesz space. But also the other side is like the other spectrum, other side of the spectrum is possible. So not only like pre-Riesz spaces basically sit between Riesz spaces and antilattices. That's what I wanted to say. So pre-Riesz spaces can be as bad as possible when it comes to the existence of the modulus, that only the elements in the cone and minus the cone actually have a modulus. But like with our characterization, we actually found every element which then has a modulus. So if I take some pre-Riesz space with a cone k and let y be some vector lattice cover of x, then we get the following equivalent statements. The modulus exists in x if and only if the modulus of ix exists in the image of x. And now comes the geometric characterization. Either x lies in the cone or minus the cone, or there exist two positive disjoint elements such that x lies in the span of those two elements. And I'll demonstrate the geometric meaning of this in an example in a bit. Or all of this is equivalent to it lies either in the cone or minus the cone, or there exists some subspace D such that the element lies in D and the image of D is a Riesz subspace of Y. So let me now demonstrate the geometric meaning of this by considering the polyhedral cone, which looks like this, one specific polyhedral cone. And it was proved by Anke, Ono, and Feng that there are only two pairs of disjoint elements, or actually, namely those two, which are marked in red color, and the green ones. So we get as a picture of all the elements which have a modulus as, of course, the cone and minus the cone, and those two planes spanned by the pairs of disjoint elements. Yes. And from this characterization of the elements with modulus, we can get to the corollaries which were to be expected, kind of. So if I have a pre-Riesz space and two positive elements, then they're disjoint if and only if the modulus of the difference exists and equals the sum. So yeah, pretty much to be expected. And if I have two pre-Riesz spaces and a positive linear map between them, then I have that this map is disjoint preserving on positive elements if and only if the modulus of the images always exist and equal the image of the modulus. So every positive disjoint preserving operator is basically a Riesz homomorphism on those subspaces generated by the disjoint elements. Yes, and then we successfully used this characterization of elements to some problems in operator theory, which were like too many to state them all here, but if you're interested, you can find them in the paper, and I'll also put them in the extended slide version. But just to summarize, we characterized some the functionals with modulus on some certain finite dimensional partial order vector spaces. We also computed the modulus of Riesz star homomorphisms if it exists on subspace of continuous functions. We also characterized when two Riesz star homomorphisms on subspace of continuous functions are disjoint, or equivalently when the modulus of the differences of two Riesz star homomorphisms exists. And we connected the disjointness of two Riesz star homomorphisms on order dense subspace of continuous functions with the disjointness of the Van Handel extension. And one next step would be now to investigate what we just did mainly for order unit spaces and order dense subspace of continuous functions, and generalize the results to the setting of some arbitrary pre-Riesz spaces. So there are still a lot of open problems. Yes, otherwise, I thank you very much for your attention, and I'll be happy to answer any questions.
Okay, thank you, Janko, for your nice presentation. I really find it very interesting, and the idea of the diagram is a smart idea. So, is there any questions?
May I ask a question?
Yes.
Yes, so this correspondence between Riesz and Riesz star homomorphisms, yeah. So you had a condition in order unit spaces.
Yes.
And in general, pre-Riesz spaces, it's false, they're not equivalent, right? So what happens maybe in pervasive pre-Riesz spaces? Is it known whether those are equivalent there?
Yes, there's an counterexample in pervasive space. It's an example for the Namioka space, which I showed here.
Pervasive, yes.
That one is pervasive, but you can define a Resolumorphism which is not a Resolumorphism.
Ah, okay.
Namely,
Okay,
just the evaluation at 0, for example.
Okay, yeah, okay, see. Great, thank you.
Okay, thank you. Is there any other questions? Okay, I think Anil has a question.
Yes.
It was a very nice talk. I very enjoyed that. I have a very general question. Maybe you can answer today or maybe later. Generally, what we expect that when we define this modulus, then we expect that positive elements, general elements have an orthogonal decomposition in general. So do we have such results? Am I clear? Means if I take a general element, say X, so can I find two positive elements Y and Z, which are orthogonal, and X can be written as difference of Y and Z?
The question is if we can always find two disjoint elements such that this element X can be written as a difference of disjoint elements. In pre-Riesz space, in general, not, because as I said, there are pre-Riesz spaces which are antilattices, and in antilattices, we don't have any non-trivial disjoint elements. So, for example, spaces of polynomials or so, there are no non-trivial disjoint elements. You only have the 0, and yes, so you can't write elements as a difference of disjoint elements.
I think, of course, your notion is a little different. I also study this kind of orthogonality and this modulus, and which includes both. So you said non-lattice, but you know that general C algebras are non-lattices. But still, it has that property. It has modulus, and we can do that. Take any self-adjoint element and we can write as difference of two positive elements, which are orthogonal.
Okay.
Of course, see.
Maybe I can answer this.
Different from what I study. Given I study them, and in my sense, every self-adjoint element will have a difference in certain spaces, of course, which I call absolute order spaces or absolute order spaces.
So I think the main point here is really that what's the definition of a modulus, right? So I think the definition of a modulus here is really the smallest upper bound of x and minus x. And that's of course not the definition of a modulus in C-star algebra, because it's in C-star algebra the modulus is not subadditive. So I think it's just a different. So the modulus in the C-star algebra is a more general or more abstract or less restrictive notion than here. I think that's the main difference.
I think I want to draw your attention. I recently proved, not recently, I think just 2 or 3 years ago, that this algebraic orthogonality, what you are talking, can be seen in terms of order theoretic. Of course, some geometry is there, some norm is there. So it's not that it's just algebraic. But of course, yes, that's why I was wondering whether this definition gives that kind of observation. And he says, in general, it's not.
Okay, yeah, I have to be honest. I don't really understand what you mean, but that's probably because I'm not really an expert in C-star algebra facts. So, yes.
I have some different papers in positivity. You can see them. Then there is a, so you have one side, you have algebraic orthogonality, and that on the other side, we have this order theoretic. And they are equivalent in certain sense, which I call absolute orthogonality actually. But anyway, so of course your definition is different, I know, and just I wanted to see a connection.
Okay. Yeah, maybe I should have a look at this paper. It's probably interesting to see.
Either you answer today or maybe some other day. It would be a good. It's a good question.
All right. Maybe you can send me the paper or the name of the paper at least. That would be nice.
Thank you.
Thanks.
Okay, thank you. Is there any other questions?
Yes, maybe one question again from me.
Okay.
So you showed those characterizations of when Resolumorphisms homomorphisms and Resolumorphisms and so on coincide in order unit spaces, and you wrote it down in terms of this representation space. Now maybe I will phrase it in terms of matrix algebras. So you have an example with the ice cream cone. So generalization of the ice cream cone would be if you consider, and that's again, of course, a special case of C-star algebras, if you consider the self-adjoint square matrices in a fixed dimension, right? That's somehow a generalization of the ice cream cone. Can one directly apply this result there? So somehow yield, let's say, an intrinsic characterization of those properties A and B in the spaces of self-adjoint matrices without using the functional representation?
Cool. That's a good point. I don't know, but maybe that's something we should have a look at, because we're always looking for generalizations of order unit spaces results. And as I said, I haven't looked much into C-star algebra stuff, but maybe
so matrices is pretty okay.
Yeah. Okay.
Don't need abstract theory.
Yeah. Yeah, but I don't know yet, but maybe that's possible.
Okay. Thanks.
Thanks.
I have a question on this slide. So here you have a characterization for in terms of lambda ones, right? So it really doesn't matter what x to it, it's just an order unit space,
Yes.
right? So is there a reason why only the domain matters? Like some idea why only the domain matters?
I think I would say it comes to like what the techniques we're using in order unit spaces. The technique is always just using the functional representation, so considering it as an ordered n subspace of continuous functions, and then using the point evaluation to get results from the functional case and back as well. And there you only need the point evaluations on the domain space. So the codomain space doesn't really matter. You use point evaluations as the main technique, basically.
But you do need that the codomain is an order unit space.
Yes. So yes, exactly.
Okay. Okay. Thanks.
Okay, thank you. I think there are no more questions.